All right, the purpose of this video is to work out some specific heat capacity problems. So the first thing that we need to be able to do is revise our equation, right? We know that our equation for Q is equal to M times C times delta T, right? With Q being joules, M being mass, C being specific heat capacity, and delta T being the change in temperature. Now, one thing that we need to do is be able to rearrange these variables in whatever whatever situation we need them. So, for example, when we need mass, we should be able to get mass by itself. In that case, being Q over C times delta T, right? And also, if I wanted to get C, which I won't have you solve that much for, but occasionally I will, C will be Q over M delta T. And then we also have solving for delta T, which is Q over MC, right? Now, the tricky thing is right here, delta T means the change in temperature, which means if I have a change in temperature, I have an initial temperature and I have a final temperature, and you need to be able to solve for either of those. So, for example, if I was to take this over here, delta T is equal to TF minus TI, okay? Now, we need to make sure that we have a subtraction problem right here, so we need to apply sig figs for the subtraction rules. Okay, so if I'm having delta T being TI or TF minus TI, I can rewrite this to be TF minus TI equals Q over MC, right? Now, you're going to need to be able to rearrange this equation as well to get TI by itself and to get TF by itself, right? Now, to get TF by itself, it's pretty simple. If I have TF minus TI, I simply just add TI to both sides, and I end up with TF equals QMC plus, so this whole thing, plus the initial temperature, right? If I was to solve for TI, again, it's mathematical rearrangement. So if I have TI, that's going to be TF minus Q over MC. Okay? You're going to need to know how to get to this equation, this equation, this equation, this equation, and this equation. Okay? If I'm solving for this, that's the same thing as just solving for delta T. But you need to be able to get to all 5 of those equations from this. Okay? That should be your starting point every time. So you get in the practice of rearranging your variables to get where you need to go. Okay? So let's go ahead and take a look at a problem. In the very first one, I am going to say a sample of water has a mass of 659.5 grams and undergoes a temperature change from 76.84 degrees Celsius to 38.68 degrees Celsius. What is the heat change in joules? Okay, so with these practice problems, you're going to have there's not going to be many dimensional analysis conversions to like change kilojoules to joules or joules to calories or anything like that. So what you have is pretty much what you get. Okay, so with that, I'm going to start off with Q equals MC delta T, right? Which if I plug in everything, my mass is 659.5 grams times my specific heat capacity. Now this is water, and water's heat capacity is 4.184 joules per gram degrees Celsius. This is the heat capacity for liquid water. Okay, ice and steam, okay, the solid and gaseous phases of water have different heat capacities. But for these examples and for your practice tomorrow, you're just going to be dealing with liquid water, which that is the specific heat capacity. Okay, so I have 4.184 joules for every 1 gram and for every 1 degree Celsius, right? You've seen me write it like this before as well, 4.184 joules per gram degree Celsius. Same thing, I just put the grams in degrees Celsius on the bottom so we can, cancel it out and stuff. All right. Lastly is our change in temperature. In this case, it is going to be our final temperature minus our initial temperature. So delta T, in this case, is going to be the final temperature, 38.68 degrees Celsius minus 76.84 degrees Celsius. Okay? When I do that math, I end up with a negative number, negative 38.16 degrees Celsius. Remember, with sig figs, I have 2 numbers to the left or the right of the decimal in this number. I have 2 numbers to the right of the decimal in that number. Therefore, my answer should have 2. Okay? So, now I do my math. I'm just going to multiply them across. And when I do multiply them across, I'm going to end up being able to cancel some units out. So my grams will cancel out, right? Because this is the same thing as writing it like that. And this is the same thing as writing it like that. So that also means my degrees Celsius will cancel out. I'm left with joules, which just happens to be my unit for energy. Okay, so when it's all said and done, I get Q is equal to negative 105,296.7197, and of course, if I'm writing all those numbers out, it's probably by mistake because I needed to use sig figs. I have 4 here, 1, 2, 3, 4. I have 1, 2, 3, 4, and I have 1, 2, 3, 4 there since I'm doing all multiplication. Now here's the trick. This guy right here is an exact number, so you do not use it for sig figs. So all you're really looking at is either the mass or the temperature for this particular instance. So with that, they both have 4 sig figs, so I need to have 4 sig figs of my answer. 1, 2, 3, 4. I look at that next number, which is a 9, and that will cause my answer to be negative 105300, in this case, joules. Okay, so that's my Q. All right. Now, of course, if you wanted to convert it into kilojoules, you would simply just set it up in dimensional analysis with 1,000 joules equaling 1 kilojoule. All right. So let's try a different one. And in this case, we're going to take a look at mass. So a sample of water of unknown mass undergoes temperature change from, we got 71.67 degrees Celsius to 6.231 degrees Celsius with a concomitant change, which means a concurrent change, with change in heat content of negative 93,230 joules. What is the mass of the water? Okay, again, starting off with Q equals mc delta T. I'm going to rearrange that to get mass is equal to Q over C delta T, right? And then it's just a matter of plugging in my numbers. Okay, once I have my equation rearranged, right, my Q is going to be negative 93230 joules over the specific heat capacity, because we are dealing with water again, so it's 4.184 joules per gram degree Celsius, right, times my change in temperature, which if I was to do the math up here, it would be, let's see, 65, it would be negative 65.44. Okay, now the reason why it's 0.44 is because I have 2 numbers to the right of the decimal here. I have 3 there, so my answer needs to have 2. So that's why it's 65.44. Okay. Now, again, number joules on top, joules on top. Degree Celsius on bottom, degree Celsius on top. So I'm going to take the joules value, so negative 93,230 divided by 4.184, and then I'm going to divide it again in my calculator by negative 65.44, and my final answer is going to be 340 0.5028237, and of course I should only have 4 sig figs, because both this number right here and this number right here have only 4, right? So I got 1, 2, 3, 4. I look at that number right there, that's a 0, so my final answer is 340.5 grams of water. Okay? So that's how you would solve for mass. And if you're wondering about this particular question here, as far as, well, why did I divide again by a negative 65.44? Remember, it's the same thing as if I did the, if I'm multiplying C by delta T, that thing is going joules, right, over joules per gram degree Celsius times 1 over the, or excuse me, not 1 over, but yeah, 1 over the degree Celsius, right? Sorry, let me fix that right there. Right. And when I do that, I'll have my joule value up top, I'll have my heat capacity value on bottom, but it's the same thing as if I multiply, let's see if I can get this without screwing this pen up so bad. Right? I'm going to do this division first, and then I'm going to take that quotient, and then I'm going to divide it again by that number right there. Could you multiply these two numbers together and then do the division? Of course you could. Right? And if you want to do it that way, you can. It's completely up to you. All right? So, the last type of problem that we're going to do here is a sample of water has a mass of 544.9 grams. What is the initial temperature of 79.84? If it gains 3,944 joules, what is the final temperature? So, again, going back to our oldie but goodie, Q equals MC delta T, right? So MC delta T, I'm rearranging that to be with delta T is equal to Q over MC, but I need to rearrange it again to ensure that TF is going to be equal to Q over MC plus the initial temperature, because I'm given the initial temperature. I'm trying to find the final temperature. Okay? So this is the equation that we're going to be using. So with that, I'm going to go with 3,944 joules over 544, the mass, 9 grams, times 4.184 joules per gram degree Celsius. Right? That, of course, will cancel out my grams, and that'll cancel my joules out. I'm left with degrees Celsius. Okay? And I'll do that whole thing, and I will then add the initial temperature. Okay? So, if I do the math out, I end up with 1.730 degrees Celsius. My initial temperature was 79.74 degrees Celsius. So with this, 2 sig figs there, 3 there, so my answer needs to have only 2. So it's 81.47 degrees Celsius. And that's my temperature final. And that would make sense, because if something is, like you look at the question, I'm gaining energy, my final temperature should be higher than my initial. My initial temperature was 79.74 and I gained energy. I should have a number higher than 79.74, and I do. Okay? So, the next one, I want you to pause the video and then give yourself a few minutes, answer the question, and as far as I'm going to give you Q equals MC delta T. The rest of the way is yours. All right? So go ahead and pause the video, work out the problem, and then play the video again, and I'll have the problem all worked out for you with an answer. Okay, so here's our key. So if I rearrange Q equals MC delta T with the temperature change, I should have TI equals TF minus Q over MC. right? So when I plug in my numbers, I end up with 92.90 degrees Celsius minus 55,360 joules over 593.3 grams times 4.184 joules per gram degree Celsius. Remember, I'm doing water, so that's why my specific capacity is 4.184. Grams cancel out, my joules cancel out, I'm left with degrees Celsius, so I'll have a degree Celsius here and here, which pops down there, and then that one pops down there. I do my difference, and I end up with an answer of 70.60 degrees Celsius. And of course, again, this should make sense because if I have a system that gains joules and my final temperature was at 92.9 and I gained joules to get there, that means my initial temperature should have been lower. And of course, 70.60 degrees Celsius is lower than 92.90. Okay, if you guys have any questions, by all means ask. If you want to, you can start on practice. You can go to the CSU Dominguez Hills website, click on chapter 6, and then it's the number 1. So if you want to, chapter 6 on CSUDH, chapter 6, and then number 1. And that'll bring about word problems just like this guy right here. Okay? If you guys have any questions, you can always email me or ask me in class tomorrow.